We are starting light, which if you're trying to study anything from beyond the solar system, all you've got to go on is light. And so we are going to try to gather as much information as we can from the light that we see. So let's first figure out what light is. Light is a wiggle or wave in the electric and the magnetic field. And one ends up causing the other. A wiggle in the electric field causes a wiggle in the magnetic field, and that keeps it propagating, keeps it moving through space. One causes the other and then back again. And because it tends to travel in a straight line, once that wave starts, we can call it radiation. It radiates out from its source. So the fancy word for light is electromagnetic radiation. Sounds terrifying. It's just light. So we've got electromagnetic radiation. And let's look at the wave. We're going to just treat light as a wave. And here we have two example waves. We have one here with a longer wavelength. A wavelength is really just the distance between the peaks. So find a peak, find another peak, find the distance between them. So that's a longer wavelength. And down here we have a peak and a peak. That's a shorter wavelength. When you have a longer wavelength, it means that that light is lower energy light. Lower energy. And that also means that as the light is traveling at you, you will see the peaks less frequently because there's more distance between them. So we could say that that light is also lower frequency. For this more bunched up wave with a short wavelength, that happens for higher energy light. And for the higher energy light, these peaks are going to come at you more frequently because they're spaced more tightly together. So you can also call it high frequency light. Oops. Higher frequency. Forgot the H. So, the electromagnetic spectrum. Spectrum just means runs the gamut, all the way from one end to the other end. Let's go from one extreme to the other. So let's start with really high energy. We're going to start with really high energy over here, and then just name all of the different categories of light all the way to low energy. So we're going to start off with gamma rays. Gamma rays are really high energy, fairly dangerous. We don't have to deal with them on Earth because our atmosphere protects us from the gamma rays from space. A little bit lower energy, and we would call that type of light X-ray light. Also high energy, fairly dangerous. You don't want to get too many X-rays. A little bit lower energy, and we have ultraviolet light. Right, sunburns, skin cancer, still somewhat dangerous. Ultraviolet butts up right to the visible, right up next to the violet. So ultraviolet is right next to the violet. So violet light is the highest energy light that we can see. And you go through the rainbow backwards. That means red light is the lowest energy of light that we can see. If it's slightly too low energy for us to see it, you've got infrared light, which really we don't consider dangerous unless you have a huge amount of it and it's going to bake you. Slightly lower energy, you've got microwaves and radio waves. Both of them are just lower energy forms of light. As a whole, we don't worry about them. We think they're pretty safe. But, if you climb up a radio tower when it's broadcasting and you're exposed to really intense amounts of radio light, yes, it can cook you from the inside. Right? But low dosage, we don't worry about it. Same with microwaves. I stand in front of my microwave all the time. So those are the 6 bands of light. 7 if you want to count microwaves, in order, sorted by energy. It's also sorted by wavelength, and it's not up here, but you could also sort it by frequency. Right? The gamma rays have the highest frequency, all the way down to radio waves, which is the lowest frequency. So all 3 of these ways, let me put frequency in here. All 3 of those ways are redundant ways to talk about energy. If you give me the wavelength, I know the energy and the frequency. If you give me the frequency of the light, I could tell you the energy and the wavelength. They're all redundant. There are several ways that light and matter can interact. Right. First, let's do transmission and refraction. In both of those, basically you have light, so there's your light, and it will interact with a material, so matter, and it just keeps going. So transmission, the light goes through a window. The light goes through the air. Right? We would call it refraction if that initial path gets bent a little bit. So like when you wear glasses, the light goes through the glass and it bends a little bit. So then we would call it refraction. But in both cases here, light goes through the material. Right? So light can go through matter in certain cases, but in other cases, matter might be able to absorb light or emit light. So let's say you've got a black t-shirt. Here's a black t-shirt. Black fabric absorbs every visible color. And absorb basically means that the light came in to the black t-shirt, and then that energy stopped being light. It destroyed the light and it went into the thermal energy of the shirt. So absorption is destroying light. Matter can destroy light. Let's say you've got a light bulb, a hot incandescent light bulb. The matter can emit light. So matter can create light. So just think of a light bulb. Matter can destroy light, and matter can create light. Right? Then we've got reflection and scattering. Reflection, we usually say, is a clean bounce of light. So think of a mirror where you can actually clearly see a reflection in the mirror. Light comes in and it leaves, and there's actually a law of reflection that says that these two angles here have to be exactly the same. But much more common is scattering. And scattering is how you can see pretty much all the objects around you. Light comes in, hits a desktop, and when that light hits that desktop, the desktop scatters it in all directions, which means that different people in different locations, there's a person, can see light from that desktop. So everybody can see the desk, and it looks the same to everybody no matter where they're located, as long as they can see the desk. We're going to spend a tiny bit of time talking about what is matter. I'll introduce protons and neutrons, but really what we're going to need for the rest of the chapter is the electrons. So matter is made up of neutrons, which are a little particle that have no electrical charge, and protons here, which have a positive charge, and protons and neutrons hang out in the center, in the nucleus. And they have almost all of the mass here, right? Protons and neutrons have the mass, and they're located in the center. The electrons have very, very little mass, and they're located far outside of the nucleus, right? This image here is not to scale. The nucleus is amazingly tiny compared to these electron orbits. Okay. The electrons surround the nucleus. And this is a cartoon version that shows the electrons on nice, neat circles around the nucleus, but it's really just an analogy. The electrons do not move on nice little orbits. Right? Quantum mechanics gets messy. Right? But what this cartoon is really handy for is it shows that there are different levels that the electrons can exist on. The electrons can exist on this orbital, let's call it an orbital, or the electrons can exist on this orbital. And that is going to be really important here in a second. The electrons are outside of the nucleus, and they have to be on one of these orbitals, one of these energy levels.